Hello everyone, this is Ron Mertens from Metalgrass and MicroLED Info in the MicroLED Industrial Association. And I want to welcome you to the third session in our first MicroLED Connect live event, virtual event. And I think we have some really good speakers this time, as always. So I want to introduce Simon, from SmartKem, the UK-based developer of OTFT backplanes. And I'm going to give the stage to you, Simon. Let's begin.
My name's Simon Ogier, I'm CTO of SmartKem, and today I'm going to describe to you about our processes for making OTFT backplanes on top of microLEDs as an alternative to the conventional way of attaching the LEDs to the backplanes. We're actually a US incorporated company, hence this legal notice at the beginning of my presentation. But actually, the majority of our operations are in the UK. They are based mainly in Manchester, where we have our semiconductor development at Blakely, North Manchester. So this is where the synthetic chemistry and formulation work is done, and some initial R&D. And then where we do all our device development and prototype development is up at the Centre for Process Innovation in Sedgefield. We do have an office in Taiwan where we do field applications engineering support and working with customers in Taiwan and other parts of Asia. So our materials are inks, which are coated from a solvent, so they're very easy to apply to build up electronic devices. So they're both dielectric inks, planarizing inks, semiconductor inks, and surface treatments. And with that, then we can build up thin film transistors in a very different way to the conventional PECVD sputtering processes. This shows the structure of an organic transistor, which looks quite similar to a lot of other transistors. Has 3 electrodes, source, drain, and gate, which are typically metals. And then there is a substrate, which can be either plastic or glass. And then the rest of the layers we develop as liquid coatable inks, which are either UV curable or just coatable and processed with hot plate baking to evaporate off the solvent. So we make a range of different materials, and they're all tailored in order to work together to provide a highly uniform, high performance transistor with very good stability. This shows some of the formulated inks that we supply, and we can supply in quantities up to say 1,000 litres per month or so, so we can support some quite significant prototype development, and they can come in a range of different pack sizes from 100 millilitres to 3.5 litres. At CPI, this is the CPI facility in the northeast of England, run by the Centre for Process Innovation, and this has a lot of prototyping tools that allow us to take the ink and to work out process routes for developing devices by thin film coating, photolithography, sputtering, wet and dry etching. And so therefore the inks can be imported into a pre-existing display line, which is used for say more silicon with fairly minimal changes to the process tool set. This just shows the process flow. It's using photolithography, masking and patterning, wet etching, dry etching, coating, UV curing, and other types of fairly standard processes that you would find in an amorphous silicon backplane. So we use a dual gate device. So it has 2 gates, a bottom gate and a top gate, mainly for exclusion of light from the transistor to stop it from changing its properties when under high illumination. So these 5 masks can be used to create the basic transistor stack with interconnects, but then you can apply other masks in order to convert it into different type of devices. And so we've done all of these types of devices like OLED, organic photodetectors, logic devices, as you can see here from this small cartoon of one of our substrate designs. And then today I'm going to talk more about the way in which we've used this process stack on top of mini and micro LED in order to make displays through the use of a planarizer with a patterned layer in it. And I'll show you some of these demonstrators later on. So the key feature of our materials is that they're processed. The semiconductors themselves are designed in the chemistry, and so the properties are determined by the chemical structure and not by any post-processing. The heating processes that are used are mainly just to evaporate the carrier solvent used to coat the liquid. So therefore, they can be processed at very low temperatures, and we've even done down to 80 degrees C for the whole process, and shown very similar process performance of the devices versus the slightly higher temperature of maybe 120 or so as our standard process flow. So what's the benefits of that? Well, there's a few different benefits which may or may not be relevant to manufacturers, but we think all of them may have some influence in the display industry, in maybe not now, but maybe in the near future. So one of them is that with low temperature processing, you have a lower energy use in manufacturing. So you don't use PECVD, you don't have to go up and down to 360 degrees C. The substrate type you can use can be a very wide choice of different plastics. So you can choose your plastic for its transparency, so no birefringence, no color in it. You can even choose substrates because of their potential for biodegradability. So that's maybe for more in kind of circuits or Internet of Things applications where you don't want to collect up all of the electronic devices after they've been used. Maybe you want them to biodegrade. You can use feedstocks which are bio-derived rather than petroleum-based, like cellulose-based materials. And typically they can be quite low cost as well compared to the engineered polyimides that tend to be used today. And then the last integration is integration benefits, and I will highlight this today in the way in which we make the micro-LED displays. Because of the low temperature, we can process the backplane on top of the LEDs rather than the other way around. And that's because normally micro-LEDs would be damaged if you took it up to, say, 360 degrees C for the PECVD process. So no doubt these types of tables have been shown many times in these seminars. Micro-LED has a great benefit of very high brightness, high efficiency, and long lifetime. And so therefore, for a number of applications, it's seen as the kind of next generation type of display with lots of benefits. One of the main challenges, again, which has probably been reiterated, is the yield of manufacturing devices, and that's because we have to take the individual wafers with the individual colored LEDs, dice them up, and then sort them into a RGB arrangement, shown here, and then attach them all electrically, connect them all to the backplane. So this is probably one of the most challenging parts of the process, is that you have to create an ohmic contact between the pads on the backplane and the pads on the LEDs. And for that, typically people will use low melting point metals to form a eutectic bond between the pad on the LED and the pad on the backplane. And these might be materials which are processed in kind of thicknesses of 2 to 3 microns, and therefore have to be patterned by processes like liftoff. And so the two challenges here for backplane manufacturers is that thermal evaporation of metals is typically not done, and also liftoff is typically not done in backplane manufacturing, because both, the liftoff causes defects, and the thermal evaporation is not used generally for large area coating, it's generally sputtering. So therefore, how do you kind of make this process more compatible with display backplane manufacturing? So the way we've thought of doing this is say, can we not move the LEDs at all, just leave them on the original wafer? So what we've done is to apply a planarizing layer so that we can create a sputtered contact down to the via of the anode and the cathode of the LED, and then process the OTFT on top. And that way we can use compatible processes for backplane manufacturing of photolithography, dry etching or direct patterning, and sputtering for the metals. And this is something we recently published in Nature Materials, which showed the fabrication of a range of different pictures of both mini and micro LED displays on top of the original native sapphire wafer. This shows a couple of videos. So on the left, we have a pitch of around about 1 millimeter. So it's a 27 by 48 display. It actually just emits light in both directions because it's on the original sapphire wafer. And the one on the right is a 100 micron pitch made on the same wafer, it's just a different parts of the wafer, and with the same process. So the processes for patterning the vias and sputtering does allow you to make a whole range of different types of periodicities, with the common thing that they both can be quite bright if you design the backplane with enough drive current. So this is just showing some of the structures here. So we have the cross section of the MicroLED wafer. You can see the pattern sapphire on the bottom, and then we planerize out with one of our dielectric materials. So you can see here the dielectric materials can go over very large steps without any kind of effect on them, and then we can just photolithographically pattern a via down to make contacts. And then you can see here the select TFT, the thin film devices processed on top. So this process has been demonstrated, but the main problem with this currently is that you're using the whole area of the sapphire wafer in order to make your display, and obviously sapphire wafers are relatively expensive at the moment. So if you want to make a very large area display, this doesn't give you an option to do that. So we think there is a good combination of the two processes by using part mass transfer, where you can put the flip chip devices onto a transfer sheet so they're spaced out. Therefore, you can use the LEDs very efficiently. You then planerize them out with a thick dielectric material and form sputtered contacts, and then build the backplane on top of that as well. And so this has had the advantage versus the current tiled approach, is that it's potentially a lot cheaper because you're making a single piece backplane. You're attaching drivers around the edge of the display rather than onto every single panel. So this is just showing the current approach of tiling, whereby you have lots of electronics behind every panel, and then each panel has to be kind of matched and tiled together very accurately. So this ends up being quite costly, very heavy in order to do, whereas this potentially can scale to a display backplane line where the economies of scale already seen in the display industry can be used for that. And even you could do plastic displays as well. So because we're forming sputtered vias and using photolithography, we can go down to very small LEDs very quickly. So in the current MicroLED TV, the LEDs are something like 34 by 85 microns, and just going down to something like 30 by 15 flip chip would be a reduction in area of 84%. So that would then give you an 84% reduction in your cost of your gallium nitride wafer. We can actually, once these things are built, we can actually remove the glass wafer, and then you can emit downwards through the transfer sheet to make a very flexible micro-LED display. Because it can be on a single piece, then it can scale to very large generation sizes. We're not using thermal evaporation on a Gen 8.5 line, and we're not using lift-off processes, which generally aren't used. For that, we think that then potentially there could be a much greater yield of the connectivity between the LEDs and the backplane, because we're avoiding these kind of metal bumping processes. And we do require some bonding between sort of gold and the LEDs, but because it's through a sputtered via and not through a eutectic bond, then we don't need to make these thick bumps on the backplane. And so from a cost benefit, if we do the monolithic wafer approach, this is just showing a calculation of the different types of displays with PPI and resolution. And so if you're using the whole of the monolithic wafer, then for something like a smartwatch at 2 inches diagonal, it would be about $83 worth of gallium nitride. But if we use the transfer sheet approach where we spread the LEDs out a lot further, then it's would come down to roughly around about $2 worth of gallium nitride. So it's a big reduction by using this chip first approach, not on the wafer. And then this is the calculations for a range of different types of displays, such as TV, it would be around about $98. Whereas currently with the 85 by 34 micron LEDs, because you've got so many pixels, so something like 24 million pixels, you'd be spending over $2,000 worth in gallium nitride just alone, let alone the rest of the processing costs. So very quickly, just go through the last part. There is a worry about organic transistors having low mobility, and obviously for high brightness that's required in displays, there are a number of factors affecting how bright your display can be. Some of these relating to the emitter, like the luminous efficiency, outcoupling factors, but a lot of it's down to the transistor. So things like mobility of the semiconductor is important, dielectric capacitance, voltages, etc. So these are some calculations that show how bright we can make LED displays driven by OTFT. So this first one is a case study showing a mini LED backlight. So with a large drive transistor in this pixel, we can actually get up to about 250,000 nits. And this is just showing a picture of the backlights behind an LCD, which is basically illuminating the panel in order to create a local dimming effect. The second one is the higher resolution 254 ppi. So this has a W over L in the transistor of 120/4, and this can generate around about 40,000 nits, as you can see here from this image. We can get higher brightness with higher voltage, but generally the operating voltage of driver chips is typically a lot less. So you don't want to go to such higher voltage, but still 40,000 nits is more than enough brightness for a number of applications. And finally, this is one we haven't made yet, but it's something which is potentially will be made in the next 2 or 3 months. And we're predicting around about 60,000 nits for this one at 508 ppi per GB. So one of the advantages of doing it this way round is, in terms of putting the TFT circuit on top of the LED, is that you can actually use up a lot of the space that's covered by the LED because the light is going downwards. So we can make the whole TFT circuit within the pixel rather than having to make it to the side and then attaching the LEDs later. Finally, this is just an example of a very high resolution one. This is more of a conceptual one because we don't have the capability to pattern down to the 0.5 micron channel lengths required for this. And this is predicts a luminance of about 1.6 million nits, but that's based upon a charge mobility of around about 2 centimeters squared per volt second. It's likely that the shorter channel lengths that we will lose a lot of performance in the drive transistor. So therefore, the brightness is likely to be much lower, something like 200,000 nits. So we think for this kind of application, then using a silicon IC bonded to a gallium nitride wafer is perhaps the best approach for those kind of AR displays. So I'll just leave you with my summary. I think I've probably used up all the time, so I can take 1 or 2 questions. Thank you very much.
Thank you, Simon. That was very interesting. You know how you pretty much do everything on the opposite way, and it makes sense. I wonder about the status of this technology. When you showed a slide with 1 millimeter pixel pitch, the first one, we saw some defective pixels. So can you tell us like how mature this technology is right now?
So I think you're probably referring to this one. So here you can see in the freeze frame there are a number of missing pixels. And this is mainly because this is really a proof of concept that's been done on using a contact mask aligner process to pattern the LEDs. And because when you bring the mask in contact with the sample, then it will generate a number of defects each time it touches. And so we think that by moving from this to a kind of a more automated projection lithography system for patterning the LEDs, then that should clear up a lot of these defects. Because these were normally bright pixels and we've had to laser these out by just breaking where there's been a bit of a defect in the lithography for patterning the LED. So I think these should improve as they get closer towards industrialization.
I see. Okay, and yeah, you mentioned here the colors, and we have a question from the audience. I mean, what do you think happens when you use color conversion? Quantum dots or phosphors. Is it going to affect the OTFT deposition or?
No, I think we are going to try that. So if we did a top emission device, then we could put a color conversion material straight on top of it. If we wanted to do a bottom emission device, then probably we'd have to remove it from the sapphire wafer or remove it from the transfer sheet first, and then do some post processing to put the color conversion materials on to make color. And I think that's quite an attractive way of making the color, I think, rather than having to sort the red, green, blue separately. So I think that the less you can do in the transfer process, the less complicated that part, and the more you can do with lithography, then probably the better, I think, for making color.
Okay, makes sense. Good. Maybe last question from the crowd. You showed some PPI, I mean, some display examples reaching up to 2,500, like 2,500 PPI, something like that, and with very high luminance. I think it was, yeah, 60,000 nits. Yeah, that's the one. Do you have any theoretical limits to the technology in terms of, the PPI or the brightness? I mean, usually people would say that OTFTs are very limited in their performance. So we'd be happy to know, like, what are the playground here of your technology.
Yeah, I think this one is a bit of a theoretical calculation, and it assumes that mobility doesn't go down with channel length, which it probably will to some extent. So hence I've said that more realistically, probably about 200,000 nits for this. But the challenge of making it this size is the photolithography. You need to pattern the conductors to around about half a micron and then have an overlay accuracy of probably about 1/8 of a micron. So you need to use a stepper system for this. So if you're going to go to the whole bother of using a stepper system to pattern all of this, a wafer stepper, you may as well make it yourself a silicon IC instead as the driver system. So I would not advocate for using this for making very high PPI. I would still stick to things like the silicon CMOS approach. I think we think that OTFT will work much better for larger area devices, ultimately for things like TV. So I think that's the market where it's going to really have the benefits for reducing cost in manufacture of TV.
I see. So this performance, I mean, you won't need this kind of resolutions. Now,
No,
another
certainly not.
question.
No, no.
So another question we have is about yields. Um, do you have any information about yields of the production of OTFTs? And in relation to that, is there any problems with repairing the OTFTs or repairing the LEDs themselves using this process?
Uh, yeah, that's a very good question. I mean, with OTFT, it's still a relatively early technology in terms of it's not yet fully industrialized, so you can't say you can't prove that the yield is there yet. But we have done a number of tests where we've made very, very large width over length devices. So, I mean, the one I've shown here is 82,000 over 3, but we have actually made some devices which are kind of 500,000 over 3 and can actually drive a nearly 1 amp through the transistor. And the purpose of this is not because there's a practical use of 1 amp driving transistors, is actually to see how big a transistor you can make without failure. And so we actually make these very large transistors in arrays on substrates and then measure them all and measure the yield. And that then tells us how much W we can make before we see faults. And even in our relatively kind of R&D environment that we have, then we have a particularly good yield. So I think once you get to the kind of class 10, class 1 environments of display manufacturing and fully automated handling, I don't think there is any fundamental limitation for the yield of OTFT manufacturing from a defectivity point of view. In terms of the repairability, there still needs to be some kind of repair process for the chip first approach. So you have to prove that all the LEDs are working before you make the backplane. So we have some ideas about how that can be done. But we think that because we're changing from the bumping process and laser welding to a sputtering process and a via process made by photolithography, then it should start off with a better yield than would be got from. So I'm not saying it will be 100.000% yield, but I think the number of repairs you will have to do before you build your backplane will be relatively small, I think.
Interesting. Okay, got it. And maybe last quick question about the mission direction. We talked about bottom emission and, um, for like, what is the preferred solution from your end? The bottom emission or a top emission device?
I think bottom emission is preferred because you can use the whole area of the the display. So here we've got quite a large LED, is getting maybe a third of the whole pixel size, and we can just build the transistors on top of it and then emit downwards. But it means you have to kind of remove it off the substrate. But that's not necessarily so much of a problem. I think you can do all the processing on top. You may then have to do the kind of the quantum dot color conversion materials first before you put the LEDs down, for instance, or you could process them later.
Got it. Okay, I think that's it for now. Maybe quickly you can answer. I mean, we know microLEDs are still emerging. Do you have any roadmap or timeline to when this technology can be actually commercialized? If a display maker would, start adopting it
Um,
right now?
my opinion is that, I mean, because OTFT is not yet industrialized, you have to go through that process of uh, working up through kind of the early stage manufacturing to prove that can be done. But we think that can be traded off with. We expect that the some of the benefits of the low temperature processability and maybe the ways of doing manufacturing the devices can maybe shorten that kind of cycle of getting micro LED into manufacturing. So we are working now in Taiwan to put these materials on a Gen 2.5 line, just to show that we can get to the higher quality. And once it's there, then it can then go on to larger size lines, and the next steps will be much quicker to tape once we've made that first transfer over from a lab-based to a kind of a pilot line. So we think that maybe it's still going to be kind of 3 years plus towards when you see anything practically coming out in the market with this. But I think we have some hopes that it's going to enable some unique types of products using OTFT in this way.
Okay, thank you, Simon.